Hello and welcome back to our channel. In today's video we will explore another area of machine learning, which is reinforcement learning, and we will discuss very interesting topics while training a reinforcement learning agent to solve a very challenging puzzle game. So I thought about creating this video when I was trying this mobile game called Street Fighter Duel, and within this game they have implemented a system of puzzle games, and while trying to solve these puzzles I thought, why not create an AI agent that would help solve these puzzles for me. And that's because the puzzles were getting harder each level, and I thought, well, an AI agent would be able to find the solution quicker and more efficiently than me. So I thought this would be a very fun and interesting application, and I hope that you find it as well. So as you can see here, the puzzle game called Shadalo Labyrinth, and the challenge is to find the path from a starting to an exit cell on a rectangular grid while covering every free cell on that grid. And this is actually a very challenging task, especially when the grid gets bigger and bigger by each level. So then let's see how we can solve it using reinforcement learning and discuss whether it is the optimal approach to solve this puzzle or not. So without further ado, let's get right into it. So before trying to solve the actual puzzle game we have, let's take a look on a more simplified version and let's discuss the different approaches that we can pursue to go about completing this challenge. So here we have a very simplified representation, which is a square grid, which has a starting and a target cell. So we're going to try to find the path from the start to the target cell. And let's at first consider that we don't have any obstacles on the grid. So for example, here we have a square grid of size 4. And we can actually create a different representation of this grid using graph theory. We can associate a vertex for each grid cell, and then as you can see we can define the edges as the connection between vertices, and by changing the layout of the obtained graph we can have a graph or a representation of the grid that is more aligned with the graph theory. But let us keep for now the grid representation so that we don't deviate a lot from the actual puzzle game that we're trying to solve. So I have deliberately showed you how to represent this grid or this challenge as a graph, and that's because in graph theory, the problem that we're actually trying to solve, which is finding the path that goes through all the cells from a starting to an exit cell or to a target cell, it is a very well-known problem called the Hamiltonian path problem, and it is actually a very hard problem to solve. In terms of we don't have an efficient or a time-efficient algorithm that can always find the optimal solution no matter the size of the grid. And that's why there are many heuristics that are used to find the Hamiltonian or an approximation of the Hamiltonian path in graph theory. However, we're interested in finding the actual or the optimal solution, and the only available algorithm to do that is an exhaustive algorithm that uses backtracking. So let's first see how we can solve this puzzle using the brute force algorithm with backtracking. And by the way, if you've tried to find the path for the current grid that is defined as such, you will quickly find out that there is no Hamiltonian path or no solution, and to make it possible we will need to add an obstacle. And let's watch now how the brute force algorithm would be able to find the Hamiltonian path on this relatively small grid. As you can see, the algorithm only took 2 or 1.5 seconds to find the optimal path. However, it would take even more time for bigger grids. To better understand and visualize that, let's see how much more time the algorithm would need to solve the Hamiltonian path problem for a grid of size 6. And here we can better visualize the actual backtracking component of this recursive algorithm. So the algorithm actually is checking for every possible path in this grid, and until it finds the Hamiltonian path or the path that goes through every cell without overlapping, it will correct itself by backtracking So when it finds a dead end without reaching the solution it wants, it will backtrack and correct itself again. And certainly here we can see that the time required to find the Hamiltonian path compared to the smaller grid grow exponentially. And that's because the algorithm that we're using is exhaustive and very time consuming. And that's actually due to something called the NP-Hardness of the Hamiltonian path problem. So now let's discuss a little bit what is the concept of NP-Hardness and how is the Hamiltonian path NP-hard or NP-complete. So NP-hardness is a concept within the computational complexity theory, and it is defined for certain class of problems that are called decision problems, where the algorithm has a certain input and the output is either yes or no. And in the case of the Hamiltonian path problem, the input would be the grid or the graph, and the output or the answer to the decision problem would be yes if there is a Hamiltonian path for the given grid, and no if there is no Hamiltonian path. And that's why the Hamiltonian path problem is a decision problem, and we can study its NP-hardness. So the NP in NP-hardness describes the amount of time required to solve the problem, and it stands for non-deterministic polynomial time, which indicates that in the current computational paradigm, there is no well-known time-efficient algorithm to solve such problem. So to better understand the concept of NP-hardness, let's start with a much simpler class of problems to solve, which is the P class. This is the class of the decision problems that can be solved in a polynomial amount of time. And for example, here we have the sorting problem. We also have the shortest path problem and the maximum flow problem in graph theory. So now let's move on to more complex problems. And we have the NP class, which, as I said, stands for non-deterministic polynomial time. And the very well-known example of this class is the graph isomorphism problem. And this is a decision problem that tries to answer the question, can we find an isomorphism between two graphs? And isomorphism is briefly the concept of one-to-one mapping. So to answer this question, we don't have a time-efficient algorithm. However, if we have a solution, we can verify it in polynomial time, and that is the characteristic of the NP class of problems. So now let's move on to the next class of problems, which is the NP-complete problems. And in this class we have the Hamiltonian path problem and many other problems such as the subset sum problem. The problems in this class are actually in the intersection of two classes, which are the NP and the NP-hard problems. So now let's first discuss the NP-hard problems. An NP-hard problem is a problem that is at least as hard as the hardest problem in the NP class. And to prove a problem to be in the NP-hard class, we need to prove that every problem in the NP class can be reduced to that problem. And the concept of reducing one decision problem to another requires further knowledge of the computational complexity theory, and so we won't discuss it here. However, you need to keep in mind that there are some NP-hard problems that are within the NP class, and there are other ones that are even harder that are not in the NP class, such as the halting problem. So now let's go back to the NP-complete class and discuss a little bit further. So to prove that a problem is NP-complete, we need to prove that it is within the NP class and within the NP-hard class. And we will talk about that a little bit more later for the case of the Hamiltonian path problem. So the classes that I've presented to you up to this point are actually under the assumption that the P class is different from the NP class. It is actually an assumption that's not been proven or rejected, and the problem of P versus NP is one of the millennium problems. So it is actually one of the hardest questions to answer. So moving on, but before, you need to keep in mind two things. A problem is in the NP class if it is verified but not solvable in a polynomial amount of time. And a problem is NP-hard if it is at least as hard as the hardest problem in the NP class. One more thing you need to keep in mind. Not every problem that requires an exponential, let's say, amount of time to solve can be classified within these classes. These classes are for decision problems. So for example, the factorial algorithm that calculates the factorial of a number has an exponential complexity. However, it's not within any of these classes since the factorial problem is not a decision problem. So let's move on to the Hamiltonian path case and let's discuss how or why is the Hamiltonian path problem an NP-complete problem. So to verify the NP-completeness of the Hamiltonian path, we need to verify two things. The first one is the Hamiltonian path problem is an NP problem. And to do that, we need to prove that the Hamiltonian path problem can be verified in a polynomial amount of time. And actually, there is a well-known algorithm that can do that. So for a given solution or potential solution, it can tell you if that given solution is a Hamiltonian path or not. And the second point, we need to prove that the Hamiltonian path problem is NP-hard, and that is mostly done by reduction. So a common proof would reduce the Travel-Salesman problem, which is known to be an NP-hard problem, to the Hamiltonian path problem, and that is basically how the Hamiltonian path is proven to be NP-complete. We won't go into details since it's outside of the scope of this video. However, if you're interested in the complete proof of the completeness of the Hamiltonian path, I will leave a link in the description with the complete proof so that you can go through it on your own. So now that you have a better idea on the NP-hardness and the complexity of the Hamiltonian path problem, let's go back to the application that we're working on. So as I've said in the beginning, we're trying to solve this puzzle using reinforcement learning. So before I show you the approach that I've chosen to achieve that, let's first talk a little bit more about reinforcement learning. So here we have the training loop. And there are two main components in this training loop. There is the agent and the environment. The agent is the component that will try to solve the puzzle or try to play the game. So the agent will have a set of defined actions, and once an action is chosen, the state of the environment will change, and based on that change, the agent will be rewarded or penalized. And then the reward or the penalty given to the agent will be used to update its Q table using the Bellman equation. And that's how the agent will learn. And through iteration and through trial and error, the agent will learn a certain task. So as you can imagine, the different component in this reinforcement learning approach needs to be well defined and needs to be well engineered for the problem that we're trying to solve. So for example, in our case, the actions that can be taken by the agent are either going up, down, left or right, given that the agent moves on the grid. And obviously the agent is not allowed to go outside of the grid, and these actions can actually be limited by the position. So for example, if the agent is in the starting cell, only the up and right actions are available for the agent. And the environment is the grid with the different information that it holds, the position of the obstacles present and the position of the start and target cell as well. We also need to have a very well defined reward system to make the agent want to reach the target cell. However, it needs to go over all the free cells before reaching the target cell, and that will actually present a challenge for us, as well as the state definition, which is the most important, as I found in this application, how to define the state so that the agent would have the necessary information so that it learns correctly how to find the Hamiltonian path. And one last thing before we visualize the training process of the agent, the Q table actually is used in the Q learning algorithm. So this table registers the different states that the agent can find itself in. And for each state, we define a probability for each action that the agent may take. And these probabilities are updated using the Bellman equation with a given learning rate. And we will see how this works when we go over the code later on. But now let's visualize how this reinforcement learning agent will learn. So for the first approach here and the first application, we have a 4x4 grid with one obstacle. And the state is defined as the position of the agent as well as the information within the adjacent cell. So it is as if the agent is able to see within the adjacent cells of its position or of its current position. So the agent would be able to see if the adjacent cell is occupied or it is free, so that he can choose to move in that direction. And I've defined a small positive reward for each free cell the agent would visit, and a very big negative reward if the agent would try to move to an obstacle cell, and a bigger reward when the agent reaches the target cell. However, that reward is reduced by the number of skipped cells. So I thought at first, let's start with this simple definition of the state, and let's see how the agent would perform for a span of 500 episodes, where each episode will end if the agent reaches its destination, or if the agent tries to move out of bounds or tries to overlap itself. So let's see now how the agent would perform. So after 495 episodes, the agent was able to learn a fairly good approximation of a Hamiltonian path. However, it skipped to empty cells, and I've tried to give the agent more episodes, and actually it wasn't getting any better. So in this case, there is some kind of randomness. So for example, we can run this algorithm again, and it would be able to find the Hamiltonian path. However, that's not assured. So as you can see here in this run, the Hamiltonian path was not found. So the agent learned that it needs to go over as many cells as it can before reaching its destination, which is a good indication that the reward system is well defined. However, it left some empty cells, and after some trial and error, I've decided to change the definition of the state and to give the agent more information about its surroundings, so it can make better decision on which direction it needs to move towards. And here in the second trial, I've added more information about more adjacent cells. So I've added 4 adjacent cells for each main direction, up, down, left and right. And I've also added a dead end detection. So this is a function that would detect for a given direction if there is a dead end ahead. And that is actually a problem that happens a lot with a bigger grid size. So this would allow the agent to not trap itself into a position where it is stuck and cannot move in any of the directions. So now let's see how it will perform using this state definition. So the agent was not able to find the Hamiltonian path, and its performance was even worse since there is some randomness in the learning process because of the exploration-exploitation trade-off, and I will explain that later. However, after some more trials, I've come to the conclusion that no matter how you defined the state with limited number of information, it wasn't guaranteed that the agent would learn the Hamiltonian path or how to find the Hamiltonian path, especially for a bigger grid size. And then I thought, why not use the whole state of the grid so that the agent would be able to see the position of every obstacle, the position of the target cell, and thus he can choose to move in the correct direction. However, I find out very quickly that was not the correct approach, simply because the state space will get very, very large and you'll need a huge amount of memory to even run that. So after some searching, I find out about the Hamiltonian path and its complexity, etc. And I thought, why not combine the two? So this solution is not by any means the optimal solution. However, my first objective was to train an agent, and I wanted to make that happen, even after finding out that going about solving this problem using reinforcement learning was not the optimal approach. So now let's see how we can combine both reinforcement learning with the brute force backtracking algorithm. So using this approach, the state will be defined like this. The agent would have knowledge about its position, its adjacent cells, as well as whether there is a Hamiltonian path based on the action it takes. So for example, let's say the agent would start at the start cell and it chooses to move up. So we check based on that action if there is still a Hamiltonian path, and if not, the agent would be penalized and the episode will end. And then we iterate over and over again. So let's see now how the agent will perform using this approach and whether is it actually guaranteed for us to find an optimal solution. And it is as expected. Using this approach, by combining both reinforcement learning and backtracking, we train the reinforcement learning agent to find the Hamiltonian path. So now let's try the same approach, but for a bigger grid size. And as you can see, the agent was able to find the optimal path within less than 1000 iteration. And I'm actually very happy with this result, even though it's not the optimal approach that should be used to solve the puzzle. However, that was my goal from the start, and it feels really amazing to achieve it, even though the approach was not the optimal one. So now let's move to the code and talk a little bit more in details on how the training process was going in the background. So first of all, here we import some libraries. Next we have this function, which is the check dead end function. It uses an obstacle map at the position of the agent and the direction or the chosen direction, and it would check if there is a dead end towards that direction. Next we have this function, which is the find path function. It is a recursive function used to find the Hamiltonian path based on these different parameters, which are the current position of the agent, the target position, the visited cells, the path, number of rows, number of columns of the grid, as well as the location of the obstacles. Next we have this function plot grid, which is used to plot the path of the agent. It is used to visualize the training process as well as to plot the learned path or the optimal path. Then we have this get obstacle map. So this function would use the grid size, the location of the obstacles as well as the agent path to generate an obstacle map. This obstacle map is used to create the state of the agent, and it is actually a NumPy array of the same size as the defined grid, and the free cells are represented with zeros and the obstacle or visited cells are represented with 1. So this is the obstacle map function. Then we have the Q-learning algorithm. So first of all we have a boolean if we want to plot the training process. Then we will define the environment. So we define the grid size, we define the grid and the entry and exit cell as well as the obstacle cells. And then we get the initial obstacle map. After that we initiate the agent position and we define the different set of actions. So we have up, down, left and right. Next we define the rewards as we discussed earlier. And then we define the Q table. So the Q table registers the different states that the agent may find itself in. And for each state, we define a probability for each action that the agent may take. So this table is basically used by the agent to learn which actions are better or which action is better in each state. Next, we define some training parameters. So we have the number of episodes, we have the learning rate, which indicates how fast do you want the agent to learn. And then we have the discount factor, which is a coefficient used in the Bellman equation. And we have the exploration rate and exploration decay. So these two parameters are used to manage the exploration-exploitation trade-off, which indicates for the agent whether it should go for a random guess or take a random action, or it should use what it has learned already. So for example here, if the exploration rate is equal to 1, that means that the agent should go for exploration, and by exploration we mean it should take random actions. So for example, at the start of the training process, we want the agent to explore the grid, so we want the exploration rate to be as high as possible. But then we want to lower the exploration rate progressively as the agent trains, and by the end of the training process we want the exploration rate to be almost zero, so that the agent would use what it has learned already to find the optimal path or to execute the task that it has learned. So then we have the for loop of the Q-learning algorithm, and this is the loop over the episodes of trainings, or you can call them epochs if you want. So first we want to check if there is a Hamiltonian path for the defined grid. However, since the agents start in the same state, we would register, or we would save this information so that we won't check at the start of each episode. And then we define the exploration rate to be inversely proportional to the number of episodes. After that, we have this part where we plot the initial state of the environment or the grid. We initiate the agent position and the episode rewards, as well as other variables that we need. And then we start the training loop. Each iteration in this training loop represents a step taken by the agent. So we advance to step 1. And then we have this getState function, which returns the state of the agent based on its position and the current obstacle map. So then we get the current obstacle map as well as the current state, and then we choose an action depending on the exploration rate, either randomly or from the Q table. Based on the action taken, we can update the next position of the agent. So here we have the next position depending on the action taken. However, we check if the agent would go out of bound, and in that case no action would be taken and the agent would keep its position during this iteration. So after that we get the next state, which is used in the Bellman equation, and we update the Hamiltonian path. So we check based on the action taken whether there is still a Hamiltonian path in the grid or not. We calculate the reward as we discussed earlier, and we update the Q table using the Bellman equation, which is as defined here, the learning rate times the reward plus a discount factor times the highest probability of the next state minus the current state. And then we make the agent move to the next position and we plot it if we want. And finally, we update the episode reward and we break out of this loop if the agent position, which indicates the next position taken by the agent, equals the exit cell. So in this case, the agent reached the exit cell. And we would also break out of this loop if the next position is in the agent path, which means the agent is overlapping, or the next position is an obstacle cell, or there is no Hamiltonian path based on the action taken during this iteration. After that, we can use this part of the code to find the learned path by the agent. And that's it. So we move on to the next part, which is plotting the optimal path or the learned path. So as you can see, if we run this cell, it would dynamically plot the learned path by the agent, and you can see that the agent here learned the Hamiltonian path correctly. And that's it, guys. So this is it for this application. I hope you find it interesting and I hope you learned something new. And if you did, don't forget to subscribe and stay tuned for next and for more videos. And until next time, stay safe.